Welcome.
I'm here with Dave Kilpatrick, and he's kind enough to
Yes.
let us,
Well, here
give
we
us a
are
look.
in front of the old Channel 7 transmitter. This is the one that was to air right up until 9 a.m. on December 3rd last year.
A red letter day.
It
Or
was.
was it a sad day?
It was mixed emotions. It was saying goodbye to the past, but also saying, acknowledging that technology changes, more efficient ways of doing things come along.
And this is all this huge amount of rack in here is the old just Channel 7.
Just Channel 7, yeah.
Just Channel 7, because there's different racks for each channel.
There are different transmitters
Right.
for the other analog channels, which are also off, and the digital ones as well.
And you work for TX
TSA,
Australia.
yes.
And you're actually a private company.
We are a private company that service the commercial broadcasters 7, 9 and 10.
Right.
Yeah.
Okay. But there is other gear here because this Artarmon transmitter.
This is a fairly
handles-
significant tower in Sydney
Yep.
because it also handles digital radio and some analog FM radio, some mobile phone cell towers and other miscellaneous services.
And all the channels, all the TV channels, ABC,
All the TV channels,
SBS.
ABC, SBS, 7, 9 and 10.
Yep.
The only one we don't handle is the community TV channel,
Right.
which comes from Gore Hill up near the TAFE
Got it.
for those living in Sydney.
Yep. But this is not the only transmitter in Sydney. It's part of a network of transmitters.
That's right. We have smaller transmitters dotted around Sydney to fill in various pockets that the coverage of the main site here doesn't fill in. And we added some more last year because of the switch off of analog. There were pockets where analog could cover, but digital couldn't. So we added some extra little infill sort of transmitters to
Right.
to help fill in those areas.
And they get a signal feed from here
From here,
via what mechanism?
basically, they have an internal set-top box.
Oh, right. Okay,
Right.
so they just pick up the
They pick up.
weak signal.
They
and
pick
then-
up what.
Yeah.
Yep. But because it's
Okay.
on top of a hill or a mountain,
Got it.
bit of
Of course.
elevation will make sure it gets a great signal,
Got it.
and then it'll pick that up, demodulate it, and then remodulate it onto a new frequency, transmit it out.
I take
Generally
it-
on UHF.
Right. I take it it's slightly better than a set-top box from Dick Smith, though.
Slightly better, but when you, believe it or not, when you actually get down to the core of it, it does use the same NXP/Philips
Of course.
silicon on chip digital tuner.
Yep.
Yeah,
Got it.
but with a lot better RF front end protection. There's some preamps and attenuation and other bits and pieces that
Sure.
help make it work properly.
And this is all powered off? It's all completely, mostly?
This is all off. This is all stone cold.
Yep.
Yep.
And we can tear it down and check this out, folks. We have all of the original documentation for it as well, which I'll be able to take back to the lab. Not all of it, but certainly take back some schematics and stuff like that. So that's all the original schematics, service documentation, testing, commissioning,
And
all that sort of.
it still has that
That smell.
old electronic smell.
Yep.
That smell of the past.
And there's stuff in there dating from the 80s we saw before.
Well,
So-
why don't we start our teardown?
Yeah, let's have a look.
I'll let you be the guide, but
All right.
let's start with this plate down here.
And that's made in Japan.
Made in Japan in, I can read that from here, June 1981.
Yep. Nippon Electric Co, of course, is NEC.
NEC.
So, yep, as most of the gear here is NEC made.
NEC were a very popular supplier of transmitters from the sort of mid-70s right through until the current day.
How many transmitter racks?
So there were three of these cabinets, or three of these transmitters, so they have sort of 3 doors each. The reason for that was when this was installed in the 80s, this was it. This was the only transmitter they had.
Right.
And they needed extra redundancy in case there was a problem with one. There was always another one sitting on standby ready to take over. So essentially one of these could be a transmitter on its own.
Yep.
A 5 kilowatt transmitter.
5 kilowatts, yep. Analog.
Analog.
Yes, which is different to digital.
Yes. Analog works on peak power,
Yes.
and the digital power is measured in an average fashion.
Right.
Yeah.
And were they automatic switch over on the 2 transmitters?
Yes.
If one failed?
Yep.
Right.
There's a control rack up the end, which
Yep.
we'll show you, that could either automatically or manually select the required transmitters to go to where.
Got it.
And all the switching for the input and output was done automatically. In days gone by, there would be an operator here to switch it off at night or switch
Yep.
it on in the morning. Nowadays, with computer control and remote control, practically you could do it from your iPhone or your tablet halfway around the world.
So they could have switched all this off by some...
They could have switched this off in Melbourne
in Melbourne with via
their
internet.
remote
Yep,
control.
Via their remote
yeah.
control, but that's not as fun, is it? So they had to push a button and...
No. They got some of their old guys out of retirement, I believe,
Yep.
to come in and actually flick the
switch. There is no knife switch.
There is no big Frankenstein
although we might be able
knife
to
switch.
show you that one on the Channel 9 transmitter
Oh,
later.
Maybe.
Anyway, we'll see. And behind you is some very serious looking fire extinguishers.
That's right.
So these are automated fire extinguishers for the rack, are they?
They have smoke sensors, and the idea is if there's a fire, the gas from this bottle will discharge and smother the, basically removes the oxygen from the atmosphere, and the fire can't spread.
In just the rack that's on fire, not
just
the other
transmitter.
In just the transmitter. So that's that pipe work.
That's that galvanised pipe work.
Galvanised pipe work. And yes, we'll take it. That is copper pipe work up the top. That is rigid coax, folks,
right.
which we'll take a good look at later.
Yep.
But all right, so we've got two transmitter racks.
We have one here,
One transmitter rack. Yep.
and then an identical one,
Yep.
and then another identical one. And yes, for those playing at home, they are all in sequential serial number.
Right.
And then down the end here, this was the parallel control rack.
All right.
And
So-
its job was to monitor the transmitters that were operating. If a fault is signalled in one of them, it can then automatically switch and place the other one online.
Got it. And with virtually, would the viewer at home know that it's been, like, would they see a glitch, or would they...
There would be a brief interruption
Right.
of transmission, maybe about a second, to prolong the life of the contacts in the actual RF switches. They're generally not switched with power applied,
Right,
because RF can cause a massive arc,
of course.
charring and burning the actual switch contacts, which could be silver or gold or some precious sort of metal to ensure a excellent contact. So there'd be maybe a half-second glitch while it turned off the power of the transmitter, flick the switch, and then turn it back on.
Right. Can
But
we have a look behind some of these
Yeah, absolutely.
puppies? Let's go. So this is the
Hybrid and phase adjuster.
hybrid and phase adjuster. Sounds impressive.
Well, its job was to take the exciter, which is the piece of gear that actually makes the RF, which we'll have a look at soon, and it splits it and switches it and directs it into the appropriate transmitters as required.
Alright, let's have a look. Oh, look at this. Coax running everywhere. And check these out. These are RF coaxial relays. You'll notice that there's a relay contactor down in there, and you'll see a little plastic shaft coming out of the RF switching can there. So that relay is just sitting there on its own and pushes the contactor of that. Can I push that in?
Yeah.
There we go. Oh, there we go. That pushes that in, and that's just an RF switch. So this is one very complicated RF switching box, pretty much.
Yeah, custom made, I would think, for this type of installation. May have even been slightly customised for this particular installation
I'm
as
probably
well.
sure it was. Yeah.
A lot of this gear, a lot of it is made for worldwide applications, and then some of it is also made for specific applications. They were very good at combining custom-made gear with standard off-the-shelf gear.
Got it.
And hence why there's so many manuals, because there'll be a manual for the standard parts, there'll be a manual for the custom parts.
And when I did the video for the switch off, a lot of people wondered if this gear could be repurposed for digital. Tell us about that. In theory and in practice.
This one, in theory, possibly, although I wouldn't like to try it. All the digital transmitters you'll find are, at least the VHF ones that I've come across, are solid state. So they're all transistorized. And we do have another old analog transmitter that might possibly be able to be converted into digital. There's enough linearity in the amplifiers to do that.
So it's all about how linear the amplifier is, pretty much. So if it's linear and wide enough bandwidth, it could be used for analog or digital.
Correct.
Is that right? Yeah. Okay. Excellent. So these are all valve-based.
These are valve-based
transmitters. So how many hours total operation on these?
80,275 plus
80,000 hours.
100,000.
Plus 100,000 because it didn't have enough.
It ticked over in 1999.
It ticked over in 99, folks. There you go. So that's how long this thing has been in continuous
Generally,
operation.
apart from about an hour per week, where they would switch to the backup transmitter when it was finally installed later on in the 80s, these would have been in continuous operation.
Right.
Only 2 running ever at a time, so the third one sitting as a standby, but they would be rotated to ensure even wear.
So these are 5, so at any one time it's 5 kilowatts to the antenna.
10.
10 total.
5 plus 5.
5 plus 5.
Yeah.
10 total.
Yep.
Brilliant. But if one of them failed, it'd go half power to 5.
Only for a brief amount of
brief
time,
period
and then
until the backup.
The auto control would sense that failure, switch.
And switch the backup. But if backup failed, then you'd only be operating on
Then you
5.
drop down to 1,
Yep.
But chances that are pretty rare.
Okay.
Yeah.
Yep.
A lot of this stuff was really well over engineered.
Right.
Maximum reliability was the key, not so much cost.
Yep.
And then of course the engineers over the years treat it like absolutely pamper it, make sure every little thing is perfect.
Got it.
Every little adjustment is perfect, which is what you want to do if you want to prolong the life of these things.
Yep. For sure.
This was in continuous operation since 1981.
Fantastic. That's a long time ago in a galaxy far, far away, folks. Can we have a look inside the auto control?
All right.
All right. That's got lobs. This is the actual one where they switched it off, right? They came in and they pushed the button.
Yep. On the news, they had someone coming in here and pushing the off buttons.
Although they didn't get it right the first time. The camera guy wanted another angle,
I
didn't
think
he?
they wanted a few more angles, so there were a few attempts.
You're right, okay. But they made sure the transmitter was disabled at that point.
That's
so
right.
It was a dummy.
It was a dummy switch off. But
So what we saw on the news was probably a fake button push.
May have
Maybe.
been. May have
So,
been. But, they always do these tricks on TV, don't they?
They do. And look at that. That's some lovely loom work there. Check that out. They've got the all individually wrapped and very nice. A whole bunch of resistors over there. Look at that. That's very nice. And this is all wire wrap stuff, folks. And we might be able to take a look at that later once we get the rack out. But yeah, it looks like some wire wrap in there and some looks like regular PCB stuff. So
yeah, and
it's an interesting mix.
And that probably relates to the customization of this thing. They would have been able to build a basic functionality out of the circuit boards and then wire wrap in the specific requirements to this site.
Now what are we going to open?
Well, let's look at let's start at the input.
The input. Let's
Down
go.
here. This is where the audio and the video come in from the broadcaster.
Yep.
And it's actually converted into RF.
Right.
Now this is what does it.
And how does the audio and video get here from the broadcaster?
Back in the day, it would have been via a microwave link.
Yep.
For Channel 7 at least, it would have come from Epping.
Right.
But now it's all centralised out of their location interstate, and it arrives via fibre optic, along with the signals for the digital.
Got it.
As well.
And that's a bit of Philips gear.
That is.
That's pretty rare here. Everything's NEC, except for this puppy.
This was a later installation to convert it to stereo sound.
Oh.
So originally this was a mono transmitter, and when stereo came along, that required this to be installed.
Right.
So it takes the left and right, modulates it down to a IF frequency.
Mm-hmm.
So what actually comes out of the modulator here is not on channel. It's not on channel 7. It comes out at an IF frequency, and then it goes through a corrector to make sure that the signals coming out of this transmitter can match the signals of the other transmitter.
Mm-hmm.
Make sure they're exactly aligned, because then when they're combined, they will combine efficiently.
So so that's audio. The left-hand side there is audio, and then video on the right.
And video.
Yep.
Pretty much through the entire transmitter, right until the very last end. Audio and video are separate.
Yep.
And they're even modulated separately as well. The audio is modulated FM, frequency modulation. The video is modulated AM.
Got it.
Yeah.
And they love drawing block diagrams on this gear. There's lots of, all the gear I've seen around here all has block diagrams all written on it, which is really quite nice.
Yeah, not only block diagrams, but these fault LEDs as well, so it can even direct you to...
which part of the... So it's got basically built-in self-test.
Yeah.
Kind of, yeah.
Really handy for when you're troubleshooting.
Yep, can imagine.
And as we look further up as well.
So what frequency is that? That's got 221.15 megahertz written on it.
I believe that is the transmit frequency plus the IF frequency.
Plus the IF,
Yeah.
right.
So when you subtract the IF frequency from that, you'll get your...
Yep. Because channel 7 is 184 megahertz, I think.
Yep.
Or was. Now, have they sold off the spectrum now, haven't they?
Oh, well, channel 7 will now be used by SBS.
Oh, SBS.
Digital.
That's right. They're going to switch it over. Right.
Which is actually active in Sydney as of 3 hours after this was turned off.
Oh, right.
Yeah.
There you go.
So they had the transmitter ready and waiting, and then this was switched off.
And there's a nice little probe here.
Yeah, now this is again part of the test and maintenance and troubleshooting. These solid state amplifiers, in the case of the audio, these two amplifiers output the final amount of power for audio.
Right.
It takes a lot more power to get the visual data out there, or the visual information. The audio you can just do with these.
Oh, okay. So there's no
ones.
further amplification required.
No.
To go to the antenna.
Correct.
Right.
There's another pair, of course, in the other transmitter to air. So essentially, there was 4 of these, all operating in parallel.
Do you know the power output of the audio transmitter?
I'd say they're 360 watt amplifiers.
Yep. And nice big kilowatt meter up there. I love it.
Yes.
Brilliant. Old school. And what's the? They've got a yellow one there, and a red is like.
Now
I guess is that like a peak hold kind of thing?
Well, these are the low and high set points.
Oh right, okay.
So there's actually a tiny little metal contact. As the needle swings past it, it goes above the low set point.
Nice.
And if it was to go too high, it would trigger off that.
It'd trigger an alarm somewhere.
That's right.
Fantastic.
Good old mechanical sensing.
Yeah.
Yeah. So back to this little probe.
Yep.
That was for probing into these different test points here to measure the current of the transistors inside.
Brilliant.
And it makes sense to have a probe rather than a 50,000 position switch.
Yep.
Yeah.
Yep. Absolutely.
So you could put your test meter onto the transistor PA current setting, and then plug your probe into the socket, and it would come up with a reading. So for the audio side of things, this is where life finished.
Yep.
For the video side of things, we're just getting started.
We're just getting started, yep.
So in this case, this is acting as a preamplifier.
Right, because it is still a 300, it's the same amplifier as the other. It's not probably 360 odd watts.
It produces enough drive to send it next door to this panel.
Yes, this looks ominous.
Well,
it looks ominous. Well, it's huge.
It's a giant beige panel, but a few things will give it away. You've got plate voltage meter.
Plate voltage meter, 7.5 kilovolts. Yes.
And that would suggest it normally ran at about 4,000 volts.
4,000 volts, yeah. Plate current.
Plate current, 4,000 volts at a couple of amps.
Yep, do the math, folks.
Bit of power.
Yep.
And then these are RF power meters to record how much RF power was going into the antenna system and if any was being reflected back if there was a fault.
Got it. And that's just
some metering for the actual valve.
Yep.
So you can measure the incoming mains.
And we do have one of the valves here.
Oh, we have some on the floor.
We will take a look at it in a second, unless we can see it inside.
We should be able to see one inside.
What's SIND absorb?
A SIND is a common impedance non-directional combiner.
There you go. I'm glad you knew that.
The SIND is actually what combines the audio and video RF together.
Got it.
So that's the last sort of block before it leaves the transmitter.
Whoa, look at this. Whoa. That looks impressive, folks. That looks powerful. And we have, there we go. Is that a schematic?
That's a block diagram.
A block diagram. I'll try and get that.
Helps you locate where all the parts are if you need to check something out or replace something.
There we go. And the 8F76R is the valve.
That is the valve.
That is the model number of the valve, which we'll be able to show you in a minute. And, oh, look at that vernier for the plate voltage. Oh, beautiful.
These will be input matching.
Oh, okay, right.
So that'll probably be adjusting a capacitor or quite literally a plate inside.
Right.
To change its coupling. This one here is pretty cool. Check that out.
What is it?
It's a little chain drive.
It's a little chain drive, right. Excellent. Now that takes it back into that, which then goes into this big beast.
Yeah, some more.
Some more trimmers there.
Okay. Let's have a look at the valve.
Let's have a look at the valve. This is the transmitter valve.
So that we took off was just the chimney, because of course these valves run really hot.
Yep.
There's a big air blower that blows massive amounts of air through there.
Mm-hmm. And so what's this single valve capable of?
Well, this will do the 5 kilowatt visual.
5 kilowatt valve. Yeah. This is actually what gets sent to the antenna here in Sydney to...
You might be able to see a bit of it through the mesh.
No, it's a bit hard.
But we just undo these and...
Whoa, there we go folks, look at that. That is the 8F76R transmission valve made in Japan, and that's the 5 kilowatt transmitter. Look at that. What is that ring around that coil?
Okay.
Around there, it's like some sort of sense coil.
That will be an inductor.
Yeah.
That will probably be an inductor. We can actually look. No, it's not. Oh, there it is. There, L201. So here it is on our little plate here. So we've got the plate voltage coming in.
Yep.
Which is our 4,000 volts.
Right.
Through a bypass capacitor, and then we've got a bypass inductor.
Okay, and that's that inductor over there.
That'll be that, yeah.
Okay.
There, this is where all the volts come in.
Yep.
Into this ring. This sheet will be... They'll form a capacitor.
Right.
Between this outer copper and this inner copper here.
Okay, and that feeds the inductor. Okay, got it.
And out it comes.
Ta-da! There it is. That is a 5 kilowatt valve. That is brilliant. And of course, the new ones are all bore in solid state. Right? Yeah.
Still very specialised transistors, but you know, there's the socket down there.
And
that's what it plugs into.
Oh, there's our socket. I'll see if I can get that, folks. There we go. Look at that. Oh, and check out the RF gaskets around the edges of that. I mean, that's just fantastic. Those all the fingers, of course. I can poke my hand in here because it is all turned off, but otherwise I'd probably be thrown across the room ordinarily if you tried to get in here while this sucker was powered on.
Now, this has been turned off for a while. The chance of any residual current is going to be pretty low, but in general practice, you would pull out the widow stick.
Right, the widow stick.
Yeah, so we got a giant fiberglass rod, nice big brass or chromium plated something, and you would actually...
huge big strap on it.
Huge big earth strap, and you would generally touch that to the high voltage parts and leave it hooked on. And
leave it hooked on while you worked on it.
Yeah.
Yeah, right. Yep.
But this thing is really well designed. There are safety interlocks galore.
Yep. Because even with that sort of capacitance, you'd get some dielectric absorption, I would have, and recharging up of that voltage, I would assume.
Absolutely, yeah.
So, you know.
But there are also other discharging circuits. When you flick off the main switch, that also puts a physical contact between the plate voltage and earth. And
physically shorts it out and keeps it shorted out so the residual charge can't build back up. Yep, sensible. And these are all interlocked switches as well. We have to...
That's right. So safety was paramount when working on these. You've got these little...
yes, the door interlocks,
interlock micro switches everywhere.
Switch,
there'll be door switches here and here.
Yep.
There'll also be an air switch as well, probably up here.
Right.
So it has to sense that there's airflow.
Otherwise it won't switch on. Yep.
All of these interlocks have to be in place before it will even apply power to the tube.
Got it.
Yep. And then to get in and service the thing, normally that key would be in position. Okay, I think we've been physically locked out because the door's open.
Oh, there we go.
Yeah,
Yeah,
no.
that's probably it.
There
There
it
we
is.
go. We bypassed. There we go. Clunk.
All right. So that would be normally in,
Yep.
and the control key would be out,
Yep.
so that you can put it
Yep.
into the control
And-
panel
Right.
and turn it on.
Got it.
So, yep, to actually get into the thing means turning it off, removing that key, and now this has been locked out.
Yep.
You would put the control key down there, flick that off, HT is shorted, mains power is off, then you can take out the rear door key.
Yep. But to actually switch off the signal, they just push the button
They
over
just
in
push the
there-
button.
over there.
Yeah,
Boring.
because you have to turn off.
Right.
You've got to turn them all off. Yeah.
Yeah. And behind this panel here is the SIND.
That is the SIND,
Can you explain that again for those who've forgotten?
the common impedance non-directional combiner.
Combiner.
Yeah.
It's just this is basically all rigid coax.
Yeah, these pipes are rigid coax. This
Yep.
is a giant empty can with these adjustable filter tuning prongs.
Yep.
And there's other adjustable sort of traps and little stubs here as well. So for
Right. Okay.
traps. But that is basically the combiner for the high-powered analog and high-powered visual RF power.
Right.
So that's why everything's so big.
Yep.
It's all at huge power levels and also at the bandwidth required to transmit the whole signal.
And these are air-cored rigid coax, so there's no dielectric. Well, the dielectric is air.
Is air, yeah.
Inside these things. So there's like a half-inch copper tube or something inside that.
Yep.
And we'll be able to show you that
Yep.
in a sec. But yeah, that's impressive.
And of course, they can get bigger. These are about 1 inch and 5/8, but they can go up to 5 or 6 inches in diameter to handle hundreds of thousands of kilowatts.
Yes, and these are some of the output.
That's right.
Rigid coaxes, and they run along the.
And you'll notice that some of them bend backwards before they bend
Yep.
over towards the switching gear. And again, they have to be all exactly the same length.
Yes, they have to be length matched.
So that length matched indeed, so
Yep.
that when the two signals come to the combiner, they're at the correct phase so that they can be combined properly.
And length matched to what, a few millimeters or something? How critical is it?
At VHF frequency, you can usually have a couple of millimeters. I mean, obviously, exact is ideal,
Yep.
but of course, the lower in frequency you are, the little bit more leeway you've got.
And how do you measure that? How do you, what gear do you use to measure that and make sure their length?
You can measure it with a TDR, so
Right,
usually
okay.
a network analyzer.
Right.
Can actually measure the length of the line. You can input the velocity factor of it as well, which
Of
with
course.
this stuff is pretty close to 1,
Yep.
being as close to an
Air-cored
ideal.
rigid coax, yeah, as close to an ideal coax as you can get.
Exactly, yeah.
And it needs to be at these power levels, otherwise your loss would be,
Your loss would be very great, yeah.
yeah.
Yeah, so the loss through this is extremely low.
Yep.
You'll get small losses at the junctions there where they actually connect
right,
together.
yes, those are right angle junctions, yep.
So there'll be a little silver plated brass bullet which goes inside the internal pipes to join them together.
And we've got some control stuff in here. Do you know what that is? Looks like we've got some bare circuit boards.
Yeah, these will be miscellaneous power supplies for various control systems and you've probably got the screen supply down there as well,
Right.
which is generally a small current power supply.
Yep.
The big power supply is the tube though around the back.
Let's have a look around the back. It's a bit noisier around here,
It is a bit noisier. We're adjacent to some more gear.
yep, which we're not allowed to look at because it's
But
not
it used to be a lot noisier in here with all of this running.
with all this running. Yeah.
You've got all this forced air coming up through these ducts, being squeezed through these the fins of the tube and around sharp corners, which makes a lot of noise.
Yep.
And even on the back of this cabinet,
Of course.
we've got a
Coming
blower
out,
as well.
Yeah, blower coming out of there.
Yeah.
And what's the back? Which cabinet is this?
Well, this is the back of the cabinet with the exciter and the
Yep.
solid-state power amplifiers in it. So what we're actually looking at here are the power supply boxes for those solid-state power amps.
Got it.
So we've got a large one here for the two audio ones, a smaller one here for the visual one, and this is actually the combiner for the two audio power amplifiers.
And they are NEC. The right angle joiners are NEC branded.
That's right.
Look at that. Whether or not they manufactured them, but they've certainly got their brand on them. Looks like we've got a couple of Look, it's just tapped into the. Oh, they're the video outputs.
No.
Sorry, no audio.
What they are.
I thought it was the same coax.
So this is your main audio output, and that will go into that SIND.
Yes.
But what these are samples of the power going along that coax. So we've got a monitor point, so you can sample. It's called a directional coupler, and you can adjust it so that you can sample a known amount of power off this transmission line, and you can use that for monitoring or power measurement, alignment, testing, whatever. This other one drives the AGC circuit for the audio, so it's sampling the output of the entire system, and that's where its AGC feedback comes from.
Manufacturing date 1981. Takaka Electric Manufacturing Co. Made in Japan. Brilliant, and everything's nicely tagged and.
Nicely tagged, so you can take one of these out and know exactly where that goes. TB2 Terminal 1, right there.
Yep. Brilliant.
And all beautifully shielded. You just don't see manufacturing like this very often.
No, you don't. And down the bottom here, there's some big ass transformers.
Yeah. So what we have down here is a 3-phase DC supply, and its job is to power those power supply modules we looked at up there.
Yep.
And one of the reasons NEC do it this way is to make these as worldwide compatible as possible. So there'll be multiple taps on the transformer. There'll be different transformers depending on 50 or 60 hertz, and that's all they have to change out to change it from one part of the world to another. And down here you've got all of the cables which interface back to that parallel switching unit.
Nice serious looking ground point down there too. I mean, what would be the ground point for this entire
for this entire building?
Entire facility, yeah.
That would be the tower.
The tower
That would be the tower, and that is really well grounded.
Yep.
And then we use that as our ground reference for everything in here.
Right.
If you look behind you there, you see those.
Oh yeah. Oh wow, look at that.
120 mil earth wire.
Oh, 120 millimeter.
Yeah.
Wow. Oh, how much would that cost per meter?
I don't want to know.
That is serious amount of copper, and they're running all over the place here.
And the idea behind that is they're all bonded to the tower in more or less a direct fashion. Lightning will see a sharp bend as an inductor or a high impedance.
Of course. So
it might want to follow that path. So it might look messy the way it's installed, but it's done that way for a reason, so that there's a direct path as possible. And the idea is to remove as much voltage differential between all the various bits of gear and the tower. So it doesn't matter so much that in a lightning strike this might be at a potential of a few thousand volts. As long as it's at the same potential everywhere, you won't get arcing
that's right.
within the gear.
All right, now the back door to our transmitter.
So, this is the key, this is what gets you in.
Magic key.
Once everything's been turned off and interlocked, of course, but check that out.
This is the back of our 5 kilowatt transmitter. Oh, look at it. There's our SIN.
There's our big empty box.
Yeah, that's our huge empty box.
Yeah.
Why does it need to be so large? The frequencies where...
Again, just for power handling and bandwidth.
Bandwidth. So, and there's some more couplers.
There's some more couplers, yeah.
Yeah.
So that is the output of the transmitter.
Right.
That's your video and audio combined.
That's video and audio combined, going up there and buggering off somewhere else.
Going off to the parallel rack, which we can have a look at.
Excellent.
And basically the back of this is all power supply.
There's some impressive looking capacitors.
Yeah.
Whew. They're big beasts. And some huge power resistors up here. They're 50 ohms each.
50 ohms.
50 ohms a pop. Yep. And it looks like there's some sort of measurement shunt, something like that.
Yeah, that'll be a high impedance network, so you can sample your HT voltage. Right. Obviously, you don't want to drive 7,000 volts directly to the panel meter.
That's right. And they're 50 watt huge power resistors. Very impressive. And down here...
Now down here we have, this is just the filament supply for the valve. Being a very high powered device, it'll need a lot of electrons. And this is a 3-phase DC power supply. which culminates up to these screw terminals here. And the reason it's DC,
Right.
most tubes, as you know, run off AC, but because this is modulating the visual carrier and it's using AM, you don't want any hum superimposed on the picture.
Right, so that's why you're using DC.
DC is the order of the day.
Yep.
So
And what about the filament supply?
it would be approximately 6 volts at 130 odd amps.
130 amps,
Yeah.
nice.
There's a nice plate on the top of the transformer there with
Excellent.
all the details.
Probably read that one later.
Yeah.
That has all the details on it. Brilliant.
And again, all these multiple
all
taps.
all the tap points.
Yep. So 50 hertz, 60 hertz, different voltage adjustments. That makes
Yep.
it world compatible.
Right. Okay, so they just sell these racks to every country.
Yeah,
But
they-
are NEC one of the major ones who do this? Are there any?
Back in the day, there were,
That's
of course.
back in the day,
Yeah.
right.
You would have found these a lot of them in Australia, a lot of them in America.
Yep.
Not so much in Europe. Over there, you had Roden Schwartz, Marconi, and other
Right.
English
Yeah.
and European manufacturers. Yeah.
I'm sure they're very protective of their industry over there. So yeah.
Yeah.
And the digital ones. Who makes the digital ones these days?
NEC.
NEC still make
is
them?
still in.
Right.
They still make transmitters,
Yeah.
and we use a few of them here.
And we'll check those out as well.
Yeah, we can.
Excellent. Great. That is a very impressive 5 kilowatt transmitter rack.
Well, this is where all the 5 kilowatts comes from.
Oh, this is the 5 kilowatts. Okay.
Behind this panel is a giant 3-phase transformer.
Yep.
So 415 volts in. We have 3,180 volts out at 3-phase, up to a rectifier stack there. DC out of there, choke
So they're huge rectifiers.
there.
Once again, they're NEC branded rectifiers.
Yep.
Brilliant.
Yeah, you'll find a lot of custom parts made for these transmitters.
And you were telling me that you're sometimes requested to switch to backup power here by the local power companies.
Yeah, because this site uses so much power, especially during hot weather when you've got everyone using their air conditioner. They can put quite a strain on the grid, so we can be requested to go off grid, if you like, by turning on one of our big diesel generators.
Right.
Yeah.
And just to help Sydney out
Yeah.
because there's too many people
That's right.
just running their air cons in their big McMansions.
And also for continuity of service as well, if we've got
Right.
a big storm coming in,
Of
if we're
course.
worried that lightning strikes might take out the power grid or wind will knock trees over onto lines, we can turn the generator on for that
And
too.
how much notice would they give you for that?
For the storms?
Yeah,
Well, for the storms, we're always monitoring the radar.
Yep.
If we have to go off grid, we get about 10 minutes.
Right.
But we can do a site changeover in maybe 2 minutes.
And what size generator have you got here to power this whole
500 kVA.
500 kVA?
Yeah.
And that's now because you switched off the analog.
Because-
That's way over power.
That's a lot, yeah.
Yeah.
A lot of power we don't need.
Oh well, you can do something else interesting with it. I don't know. What
I'm not
can
going to
you
make any suggestions.
do? I'm surprised there's no flux capacitor in here. I'm just.
I wanted to install one.
Yeah.
You've got the shirt on.
No, I do
yeah.
have the shirt. Look. Yes. There we go. Brilliant.
No, we've just got regular capacitors.
And that little capacitor there, 4 microfarads, 6,000 working volts. There you go. Awesome. All right, and what have we got here at the end of the rack?
Yeah, so this is where the 3 separate transmitters come in to be switched, selected to air, and eventually combined. And you can also direct the transmitter that's not to air into a test load if you want to test it prior to putting it on air, or just for maintenance. And in fact, you can direct the entire output of the entire system into a test load as well.
A 5 kilowatt test load.
A 10 kilowatt.
10 kilowatt test load.
That's right.
Brilliant.
So the 3 transmitters come in. There's patching available on the panel. So if one of these switches were to fail, you can switch around
Right,
it.
so there's 3 of them.
Yeah. So 1, 2, 3 for each transmitter, and they're interlocked in such a way that the correct selection of transmitters can be made.
Right. And you can
switch.
just turn the dial, and that's a manual, but you can do it automatically. You can do it
You can
via
just
the
flick
control
it around
panel.
and
Yep.
turn it. Yeah.
Nice. And that's just a huge, big physical
It's a
Sweet, it's
motor-driven RF switch. Yeah.
motor-driven RF switch.
That's right.
Very impressive. And you can see the diameter changes in the coax. You've got to remember, folks, this is not, you know, there's not liquid flowing through here. These are all coaxes.
That's right.
Rigid coax cables.
So this is the end of the journey for the transmitters. We have the number 1 transmitter input, number 2 transmitter input.
Yep.
And the number 1 transmitter will arrive. Now there's a bit of, because there's phase shifting that goes on here as well, which is why the length of these lines, the phasing between the transmitters is critically important. What comes in here will be considered at 0 degrees. What comes in here will be at 90 degrees. When they're combined, they both come out there.
Right. And
if there's any mismatch whatsoever, that will come out this port, which is then sensed and goes into a little reject load sitting down there.
A reject load.
Yeah.
Reject load. Look at the size of the reject load.
In practice, there might be a few watts.
Oh, for a few watts,
Yeah.
right. But you have to cater for...
In utter catastrophe, you could end up with all 10 kilowatts in there. But generally, the protection circuits would kick in and stop that from turning into a flaming mess.
Right, yeah.
But yeah, you're absolutely right. The diameter steps up because that's 10 kilowatts going out.
And there's our final output couplers that they're sent in the output. That's the final output signal.
Yep.
Yep.
And again, that's patchable on the front panel.
Oh yeah, so because it goes, you see it goes out there, and it actually goes down into the front panel, and we can walk around and take a look at that.
Yeah.
But yeah, then it eventually goes up and it transitions into rigid copper instead of the much more expensive copper one. I guess these would have been the original ones installed.
Absolutely. This any of this aluminium stuff is original.
Yep.
And it would have all been cut and labelled, and every single piece would have been made at the factory for a specific position according to the installation drawing.
Yep.
So they supply it as a ready to install pre-made kit, and you just add your own.
That's a hell of a job. And there's the final output. It goes all the way along there. Can we follow it?
Yeah.
Here we go. Oh, and we can see some trends. There's a cricket. There we go.
England not doing so well.
England not doing that great. This is the old. Are we allowed to view?
This is the old. This is the old NEC backup transmitter for Channel 9.
Channel 9.
It's also 10 kilowatts.
Yep.
Physically a lot smaller because there's no redundancy in it. It's just one transmitter.
Right. Okay.
But a little bit more modern too. This would have been maybe 1986.
Yep. Okay. There we go.
There we are. Look. A little plaque down here says 86. There we are.
1986. There we go. Yep.
Same tube, pretty similar as valve as the old ones.
Getting blown by lots of fans here, folks. There's just tons of other gear around here, and lots of other stuff I'm not allowed to show you. But anyway, we're following. We can see the end on the rigid coax there, which we'll show you one actually down on the ground in a minute, but there's one that's not terminated there, and you can see the copper inside it. Yeah,
we've already started pulling out some of the old analog gear.
Right, yep.
To make way for a new SBS transmitter.
And here we go. Explain this, because look at this. This is impressive. Look at the size of those rigid coaxes. Tell us, Dave.
All of this is still operational. This is all part of the digital setup. And this is where each of the individual transmitters are again combined to one single signal that goes up the tower.
All of the different channels. Look.
Yeah.
They're numbered 6, 8,
6, 8, 11, and 12.
12. And so they're actually at each stage they're just added. That's why they're cascaded. Is that correct?
Right. Yeah.
So it comes into one.
So
that's impressive.
That's where analog used to connect into.
Ah, right.
Yep. So that's now been terminated. That's just a little 50 ohm.
They've got a little 50 ohm. They just turned off analog and whacked in a 50 ohm terminator.
Correct. Yes.
Great.
But each of the digital transmitters come in. It's cascaded along. Again with this much bigger.
Yeah, that is a massive rigid coax. There's nothing inside that except another smaller one in diameter. That's unbelievable.
And it all culminates into this one piece, which is then split. So there's a big power divider there, and that's split to go up 2 feeders up the tower.
And that's what actually goes up to right up the tower up to the...
Approximately 180 metres up in the air.
180 metres.
Approximately, yeah.
Fantastic. And they're huge, massive interlocks, so you can switch. So there's two antennas up there effectively, it's two halves.
There's an upper and a lower. And the reason for that is if through lightning strike or some sort of other damage, if half of it's damaged, we can then put the other half into full operation at slightly reduced power. And because these coaxes go up the tower and they're exposed to the elements, you don't want any moisture in them as well. So we actually pressurise those cables with dry air. And that's what this contraption does.
And so that's the dry air.
Yeah.
Right.
So it's just an air compressor. It goes through a desiccant dryer, and then pressurises the lines so that no water can get in. If there's a crack or a leak, it just blows air out and stops the water from getting in.
Right. And what are we transmitting at the moment? Look at that. 50 full scale deflection, 50 kilowatts. Fantastic.
So we're just under about 5 kilowatts.
About 5 kilowatts on that one.
Remember, that's half.
Yep.
So there's another 5 kilowatts up the other antenna.
Up the other antenna.
Yeah.
Brilliant. Have you ever had to actually switch them like that?
I haven't, no. Oh, there's the air dryer going.
Oh, there we go. No, that's not the antenna exploding, folks. And so, yeah, that's very impressive. So this is the active transmitter for just the digital.
Just digital now, yeah.
Just digital at the moment.
Yeah.
Okay.
And that's what the back of these units are.
Oh, right. And what is this beast?
Oh, this is more just more switching.
More switching.
Yeah.
Yep.
You'll find there's a lot of switching, a lot of patching available just to get things back on air if there's a problem with anything.
Yep. And this is the SBS.
Yeah, and this is all about to go because SBS analog no longer exists.
Right. And
SBS digital is about to change to channel 7.
Right. And what's this impressive looking thing?
It's not a cyclotron. It's not a particle accelerator.
Right.
This is a UHF combiner. And
combiner.
This is all basically waveguide. So it's all.
That's all. Oh, right.
It's not like this where there's an inner conductor. It's just hollow.
Just wave. Yeah.
Yeah.
Wow, that is.
And so quite literally, the splitter is that.
Is that? That's a splitter.
It physically splits it. Yeah. And then converts it back to normal coax there.
Right.
And again, just a smaller version of what was up the road or up the hall. Splits it into 2 antennas and goes up the tower.
Got it. And is this the? I've got some discarded panels. And is this all the power for?
Yeah, this is some of our power switching. This is the generator control. So it does the changeover sequence from mains to generator. Mm-hmm. It does it in such a way that the generators will synchronise to the grid when they change. Yep. In either direction. Got it. And then down on the floor is actually some of the parts.
Some of the rigid coax.
From the analog transmission chain, which is just recently discarded. So
let's take a look at those.
Yeah, so this is what the rigid.
Here's some of our.
This is some of the rigid coax.
Yeah.
And basically just an inner conductor. That's what carries the actual power.
Mm-hmm. And it's got a separator in it.
Yeah, it has these Teflon spikes.
Mm-hmm.
And that basically holds it up. If it's a long run, you don't want it sagging.
No, sagging, of course.
Even though it's pretty tough as it is, but over a long run, you don't want it to sag. So that'll
So they'll be every metre or half metre or something?
Spaced at regular intervals. Yeah.
Yep.
And that just
goes down like that, and that is that's probably the lowest loss coax cable you can get.
For this sort of application,
It's just ridiculously expensive because they're a 2 millimetre thick or something like that. They're it's just air dielectric, and that is the best way to transmit kilowatts. Mm-hmm. And fantastic.
That's up to a certain frequency, and then when you get up to really high powered, high frequency stuff, then waveguide tends to be
better than got it. But at sort of the few hundred megahertz we're looking at here, it's
a broadcast. Yeah.
What is the antenna capable of transmitting here? Do you know?
Oh, that's a good question. It's certainly sized so that every single transmitter we have here can be comfortably put to air.
Right.
So that was analog and digital.
Yep.
combined. Of course, now with just digital to air, it's massively oversized, but
Yep.
you know, a little bit of headroom is not a bad thing in this game.
And it's all horizontally polarised.
Television
Sydney.
is, yes.
Television.
So
Sydney,
if your antenna's pointing at this tower, then it's horizontally
it's got to
polarised.
be horizontal. I went on a holiday a couple of months ago, and I drove through a town, and all the antennas are vertical.
Vertical, yeah.
Freaks.
Yep.
Freaks. I thought, no, they've installed them all wrong. No,
you can get vertical ones.
Yeah. What's the advantage and disadvantage of both? Do you know?
Sometimes it can be due to geography.
Geography.
So your vertically polarised signals might work better in different types of terrain.
Right.
Or with digital transmission, where you can have, now this is interesting, I'm not sure if you know this, but the UHF transmitters around Sydney all transmit on the same frequency.
Right.
In what's known as a single frequency network. Now you can't do that on analog, you can do it on digital because of the way the digital scheme works. So you can have transmitters at Manly and at King's Cross all working on the same channel and all transmitting the same data, and they can be timed so that the interference zone might sit above the harbour.
I got it.
Yeah.
Right. Impressive.
So you might use vertical polarisation if you've got closely spaced transmitters, and that vertical polarisation might give you an extra 25 or 30 dB of separation.
Got it. Yep.
When you change the polarity of the antenna. These are 3 dB couplers, so just as we saw on the back of the Channel 7 transmitter,
Yep.
these can be used to either split or combine high-powered RF signals.
Got it. And there's the, check it out. That's a Teflon spacer.
Teflon insulator, yeah, and
Yep.
this will just be silver coated brass.
Silver coated brass.
Yeah.
Wow, that also cost.
And then
a
you'll
bit.
have one of these sort of
Yep.
brass machined bullets, as they're called,
Right.
and that's what the inner conductor slips over.
And tell us about this, because it just looks so impressive. The Houston Fearless Corporation, or is Fearless, or is it's Fearless. There you go. They're Fearless in Los Angeles, Carolina. I wonder if they still exist. But tell us about this.
That's a rotator controller for a steerable antenna.
And for
azimuth and elevation for television OBs or this remote reception. Yeah.
Right. Okay. So is that used anymore here?
I don't think that's been used for a long time.
Yep. It's just sitting in the rack there.
That's right.
Fantastic. With some very much older gear as well.
Yep. From some old Australian-made microwave link gear. That's old STC.
Oh, STC. Right.
Yeah.
Yes, it is. Standard telephone and cables. There you go. Oh, classic. They calibrated that in '92.
No longer used.
Yeah. Although it's still on, still switched on. I can see some LEDs lit up. So, yeah, it's all on. Don't know what it's doing though.
Not much.
Warming up the room. And yes, folks, I am allowed to take the gear and keep it because they don't want it anymore. Go figure. Well, got my screwdriver, so out it comes, the old analog transmitter. I can take it back to the lab and tear it down in my own good time. Beautiful. What a score. And yeah, I'm not kidding. I'm allowed to keep it because they're going to scrap all this gear. It's all going to be scrapped. They'll get all they'll sell it for scrap metal prices, pretty much. It's a real shame. So what can we do? Does this just pull out? Oh, that feels like it's on slide. It is on sliders. Oh, I love it. Look at that. There we go. Brilliant. Fantastic. I'll whack that in the boot of the car and we'll take it back to the lab and yep, you'll see some excellent teardowns coming up. Beauty. There it is. It's all mine.
All the back panel.
Beautiful. The old Channel 7 analog transmitter. Fantastic. And there we go. Oh, look at the switches. Oh. And that's the underside of the transmitter panel. Oh, cow button. There we go. And yeah, it's all beautiful. Look at all those coaxes and various sensor modules, I take it, or splitters or whatever. Not sure what that is. What's that? Oh, that's the meter. That's the panel meter. There you go. Oh, look at that. There we go. We actually have a PCB in there somewhere doing something. So yeah, that's just the PCB for that front panel there for the main transmitter control, and that would handles all the control and interlock, and some fault sensing as well. So there's some in-circuit testing. That's the final output switch.
That's where it transitions from the rigid copper to what's called a semi-rigid coaxial cable.
Yep.
Which, as I said, was
and
pressurised.
And it goes out the door. And whoa, here we go.
Out the door.
Out the door and
up the tower.
Here, folks, is the tower. So they're our semi-rigid.
Yep.
Coming out. And as long as you keep the bend radius under a certain amount, you're good to go. You're good to go. So, but that goes all the way up the tower, which we'll go to the centre and have a look, but that's the main tower.
And there you go. And there are generators, the green boxes.
They're our backup generators.
Yeah.
Awesome. Now if we take a look inside the old channel 10 NEC transmitter, then yeah, we actually have some real electronics in here, folks. So I'm not sure what that one's doing. Any idea there?
Yeah, that's the detector board for the various directional couplers. So there's the sniff points from the RF cables. They'll come in here, they'll be detected and converted to a linear DC voltage for
and
metering.
On the back of the door here, well, let's get in here like this. And
that's just the back of the LCD display.
That's the LCD display, nothing interesting in here. That's
the transmitter controller.
Yep.
The CPU.
And of course it's an NEC processor.
Yeah.
There you go, look at that.
But we do have
a
little FPGA.
There's an Altera FPGA. Okay, no, that's a CPLD, I think.
CPLD, yes.
Yep.
FPGAs probably wouldn't have existed.
No. And this is quite fascinating. I like this logic. I presume it's a TX control unit.
Interface to the rest of the transmitter.
Interface to it all.
Yeah.
Look at that. Lovely. Beautiful. So there you go. We do have some electronics in these sort of beasts, and even more here. Check it out. What's this?
This is the exciter.
The exciter.
Yeah. So rather than having an entire rack full of bits and pieces, it's been condensed. This is probably from about 2000, so a few generations. Yep. A few generations on.
Right. And those cars just slide out and yeah, there we go. Oh, look at that, beautiful. Look at those RF cans there. Fantastic. MSO, made in Japan. NEC, I mean, how big must the groups be at NEC that just design all this stuff? And how many would they sell? I mean, it's not high volume stuff.
No, it isn't, but it's high reliability.
Yep, yep. So they charge a fortune for it.
They do.
Oh yeah.
you would get another 10 years of use out of this easily.
Yep.
No problems.
Have you got any idea how much, like, you know, all this rack gear would have cost originally? Any inkling?
More money than I would care to think.
Yeah, that's the correct answer. But insignificant in the scheme of things, really. So there you go. That is the channel 9.
Channel 10.
The channel 10, sorry. Channel 10 transmitter. Ta-da! And that one's also going to be scrapped?
Maybe not.
Maybe not. You probably
keep this one.
Okay.
May be able to turn it into a digital transmitter.
Of course, right. Yeah, we could recommission it. And check out these huge jumpers here with the the antenna in and the channel 9 transmitter out there and the test load. So the channel 10 transmitter output can be switched through to the test load. Brilliant. And there's a control panel for, that's just the cooling system.
This is a water-cooled transmitter.
Yep.
So the water comes in.
Right. And there's more power amplifiers that we saw on the channel 7 one, but these are
the channel 9 transmitter.
Channel 9 transmitter.
And again,
that's the exciter. Woohoo! There it is.
There it is.
More. Wow. Beautiful. But just the engineering that goes into producing all this is phenomenal. Look at that. And some rigid coax on there as well.
Ah, yes.
Yeah, there we go. There you go. They're headed out there like that. Rigid coaxes all around. So this could be reused, maybe.
Bits and pieces.
You're right.
Yeah. But these just pull out.
Yeah, they're just. And there we go. And they're modular. Look at that.
That's right. So power, RF, and water.
power, oh, and water as well. Okay,
These are water
yeah.
cooled.
Yeah, so there's our water.
There's your water, there's your power and signalling.
Yep. And there's your RF.
There's your RF out.
Wow, ooh, that's impressive. Oh, that's pornographic, really is. And that one's data 2000.
Yep.
There you go, pretty modern. And here's what the antenna looks like up there. Can you explain that, Dave?
Yeah, so
these are the DABs.
So this is the upgrade that was done in 2009 to add DAB. So there's the horizontally polarised radiators for TV.
Yeah.
And the vertically polarised radiators for DAB.
Right.
So
Yep.
they're two separate antenna systems that share a common bay, a common reflector panel.
Right.
And then just above that you can see the bottom of the UHF panel array.
Yep, and
that's approximately 200 metres in the air.
200 metres up.
Mm-hmm.
Fantastic. Pumping out 10 kilowatts. Or thereabouts.
Or thereabouts.
Or thereabouts, give or take. Fantastic. Unfortunately, we can't get up that high, folks. We're only allowed to go up to like 80 metres or something. So, well, that's what it looks like. Got the transmitter. Catch you next time.